All right, I'll get started now. So a few, so I'm going to cover a number of things ranging from the, very directly related to class to more abstract material. So I wanted to spend a bit of time on the second homework. How many of you have looked at the second homework? Okay. How many of you have not looked at it? All right. So homework 2 is asking you a number of things about the CPU in lab 1. Speaking of which, I noticed that I didn't check this morning. As of last night, 4 of you had changes to emulate.c pushed to the GitHub server, and 2 of you had changes to test.c. That's given that there's, it would be useful to get, well, this is a pattern I always see. The master students get started on things earlier than the undergrad students. But if you get some code done now and push it, one of the things I will be doing is periodically I do look at everybody's repo, and if I see a mistake that a lot of people are making, I will talk about it in class, or I will send something out on Piazza or something like that. In general, the earlier you start, the less work you'll have to do. Okay. Okay, so there's 3 parts to the second homework. The first gives you a couple of instructions. It gives you the hex and it gives you the bits, and it says, what instruction is this? Now, this is the same answer. This is the same thing that your code for lab 1 is going to have to be figuring out. You'll need to look at the first bits that tell you the instruction, or tell you that it's an arithmetic and logic unit instruction, and there's a set of other bits. You'll have to look at the fields in it for the register numbers. Once you figure out where to look in the PDF for things, in the lab 1 PDF, it's a pretty straightforward mechanical question. And as I said, it's something that you're going to have to understand this in order to complete the lab anyway. So you might as well, get a small amount of practice on it. So I forget. I think okay. So the second question, we've got this in memory, these 4 locations, and this location, this is a call instruction. Those, I believe I'm remembering it correctly. If not, whatever it says in the homework. So what happened, and it's asking you what happens when we execute one instruction with this in memory and our registers starting out as this. And given what the instruction is, the only registers that matter are the program counter and the stack pointer, because call is going to push an address onto the stack, but it doesn't, and so it modifies the stack pointer. Any instruction is going to modify the program counter, but I don't see R0 through R7 here. So what's the new value of the program counter going to be after this instruction? Yes. Well, the program counter started at 1,000, and so the first thing it does, so this is the execution loop, is just fetch an instruction and execute it. So what what value are we going to fetch for the instruction? If the program counter is 1,000 hex, what value, and here's our memory off on the side. Yes, it's going to fetch 8,000, which is a call instruction. Now, what if the instruction is call 1234? What's the address of the next instruction going to be? In the back? No, someone else? Yes. 1004. No. What address does it have to be if we're going to call? Well, yes. That's the purpose of this instruction. The end purpose of a call or a jump is to finish up with the PC set to that address. And that way, the next instruction will be fetched from, in this case, the beginning of that function. In other words, that's how call works. Is, again, this is part of the, there's no magic in the CPU. In fact, there's so little magic in it that it's doing things that are dumber than you think it does. This, all that the call instruction does in the end to get to address 1234 is it sets the program counter. And then we start all over on the next instruction with no memory of the previous one, but we've changed this. And so now our function over here is executing. Questions on this? Okay, now the thing about call is that it doesn't just jump to that address. There's a jump or go to instruction, which all that it does is changes the program counter. That gets used in, in constructing if statements and stuff like that, branching from the bottom of a loop back to the top or something like that. But to call a function, we need to save the return address. So, you know what? Well, in this case, what's the return address? Yes. Well, it's a 4-byte instruction, so yes, it's program counter plus 4. Okay, and forget about the fact that I should have had a bit more space here so that it looked like a legitimate place to return to. In fact, this is going to crash afterwards. So this is our return address, and so there's an important step that call does. It pushes this return address. And so how do we push something onto the stack again? Do I see a hand over? Yes. Decrement what? Yes. And then what do we do after we decrement the stack pointer? Yeah, we use the stack pointer as an address to store the value. So in particular, we're going to decrement the stack pointer, and then we calculated our return address, which in this case is that's why this is lousy, because everything ends up falling on top of each other. But we are going to store the value 1004 at this location. I forget, the homework may have started out with, it may have had 1008. I forget, I hope it did. So that's how call works, is it pushes the address of the next instruction onto the stack, and then it jumps to the function. At the end of the function, we'll use the return instruction, which pops an address off the stack and jumps to it. And so all that a jump is setting the program counter so that the next instruction will read from that address. You know, we don't actually look at the address when we jump to it. You know, the call instruction stores to the stack, and the return instruction, you know, reads from the stack. But, you know, but again, everything works in a way that each instruction is just a standalone thing. You've got what's in memory, you've got what's in the registers, and, you know, the CPU can't see the past. It can only see what's in its registers and what's in, you know, a memory location that it's looking at. And it can store into memory, it can change its registers, you know, it can read from memory. All right, the last one is about how would we generate code to actually do, you know, in this case, 2 very simple lines of C code. So in order to do this, how can, where does the data need to be? Right now we've got, you know, this says that we want to take the value that's in Y, and Y is actually a memory address, you know, is located in memory at this address. Yes? Okay, that's fine. So in order to add something on this CPU, where, you know, let's say Y contains, I don't know, 17. So X contains 17. Before we can add something to it, you know, if X is in memory here, what do we have to do? Where does it have to be before we can use the add instruction? Can we just say add whatever is in location 1000 to, yes? Yes, yes, because this CPU, like the CPU in all of the, anyone who has a Mac, unlike the CPU if you've got an Intel machine, this CPU doesn't have any instructions which access memory to do anything other than load, store, or push and pop. So let's start, and we pick a register. Okay. Now, if, I don't know, this is something that you'll only know if you've read the documentation for Lab 1, but how do you get a constant value 5 into, I mean, we need to get that 5 into a register now. So does anyone remember the instruction to get a constant value into a register? Anyone? All right. You know, if you look through the documentation for Lab 1, you will see that the only instruction that there's a set instruction, and the whole point of that instruction is to put a constant value into a register. You know, it's a 4-byte instruction. You know, and so when your fake CPU reads the instruction and it says it's a set instruction, you're going to read the next, you know, the next word from memory and put it into a register. So here, I'll pick register 1. We're going to set register 1 to 5. Now, obviously, we can do our add operation, our instruction. Are we done now? We now have the result in register R2. Is that good enough? Where is the result supposed to be when we're finished with this line of code? Yes?
In memory at 1002.
Yes. And so, someone else, how do we get it there? Yes. Since this isn't a real machine language, assembly language anyway, you know, if, you know, some sloppiness in how you do it is fine. This doesn't exist outside of Lab 1, you know, and this Blackboard. You know, so this is, in fact, what a C compiler would generate if there were a C compiler for this CPU, for this line of code, if these two were global variables. You know, because for the global variables, we know exactly where they are in memory, and we can just read values in, we can do operations on them, we can store them back. So here, for this one, we have a pointer variable, p. And so the forget exactly. The compiler knows the location of p. You know, I think, like I said, it's at 1004. I forget. It doesn't know the value of p. Just like over here, it knew the location of x, but it didn't know its value. So it has to read p in from memory to a register. Now, if we have the value of p in a register, you know, let's say the value of p is 1,000 for a nice round, and 2,000 for a nice round number. What's the address of let me back up. If the address, this is the contents of a structure of type struct ABC. It's just a chunk of memory, and the first field in it is field 1, and the second field in it is field 2, and each of these is a 2-byte field. So if the address of P is 2000, what's the address of P points to field 1? How much do we have to add to this pointer to get down to here? Come back. Is it a 2 would put us here. Field 1 is at the very top of this structure. There is no space between the beginning of the structure and field 1. So if we have the address of P, that's also the address of the first field in P. There's no header. There's, you know, if you want some sort of header in your structure, you've got to put it there. You know, instead, this is exactly how it's laid out in memory. And so, you know, a pointer to the beginning of it is a pointer to the beginning of it. And the beginning of it is this field. Now, C is actually going to complain if you try to interchange the two things, because it's actually quite useful to keep people from switching pointers to integers and pointers to, struct ABC. Because if you accidentally assign one to the other, you're probably doing something very wrong. But at the level of the CPU, these are just addresses. And so the address of field 1 is going to be 2000, and the address of field 2 is going to be what? Anyone? Yes? Exactly, 2002. So the compiler keeps track of all this fancy information like, that P is a pointer to a struct ABC, and this is a pointer to an integer, and you can't mix it keeps all this higher level type information and names and so on, so that, in ways designed to help you, produce, well, it's C, so not so it'll help you produce reliable programs, but so you'll be at least less likely to, shoot yourself in the foot. But the CPU underneath doesn't care about that. It just knows about numbers. In this case, this number is an address. It's the address of the whole structure. It's the address of the first field in the structure. And if we're going to get P points to field 1, we're going to have to we're going to have to first load the value of P into a register. Then we're going to have to add 2 to it. And then in other words, P doesn't contain the address that we need. It contains something that we can figure out that address. We load the value of P, we add 2 to it, and now we have the address of P points to field 2. Now we can finally load P points to field 2 into a register and add 4 to it and store it into X. So that's, and yes, the CPU is, it's, these steps are painfully simple. In fact, they're a little bit worse for our CPU than they would be for a lot of others, because there's a step that, because I made the CPU slightly less powerful, so there'd be fewer steps in completing the lab. But, so that's only going to show up on, on this homework question. But questions on this? Any? All right. Any question? Any last questions? No. Okay. So, I guess this all seems very low level, and I can kind of promise you that once Lab 1 is done, we will, probably we will leave machine assembly language behind, and and you probably won't have to ever touch it again in your career. But the point, what we're trying to do in this part of the class is really understand how the computer is working underneath. And, to impart enough knowledge so that, if you really needed to know how it was doing something on a particular CPU, you could go and figure it out, and you would know where to start. For the simple things like this, it's really kind of the same for, even a modern complex CPU. And if you ever take, I don't know if any of you are going to end up taking a compiler class, but if you do, that's probably going to be about 10% of one of the lectures. But yes, that's what generates assembly code is compilers, in 99.999% of the time. And and they, and I'm trying to give a small example of how, in fact, that compiler translates, the code that you and I write into, into these instructions. All right. So, some more C and Unix stuff. So, one thing I've realized, trying to, teach anything about C is that a lot of what gets considered C programming knowledge isn't about the language itself. It's about the standard patterns that people use with C. In particular, I mentioned in the last lecture the caller allocates pattern, where you see, in particular for strings, you see these functions where the, where the library function doesn't allocate memory. Instead, it takes a pointer and a length, and it will, return a value in that buffer that you provided it, while respecting the length, not overwriting it. So the first thing about error handling is that C has no concept of exceptions. Your function returns a value, or it crashes. There is no graceful way to do. There is no way for your program to continue without that function returning a value of the type that it was declared to return. Which is actually kind of a problem, because typically you've got, two modes. There's two things that can happen in a function. Either it returns what it was supposed to, or something goes wrong. Now, in a lot of cases, the way we distinguish this is by a distinguished or reserved class of return values to indicate an error. So in particular, allocation functions pretty much always return null if they're, if they fail. That's easy to check for. It can be a bit problematic for more complex things, because you only get one error value, and you might want to know which of several possible errors went wrong. So Unix provides a basically a kludge, a side channel that lets you know which of several possible errors that the failure was. That's kind of ugly. In this case, it's pretty clear what the failure was. It was an out-of-memory error. But if you had a function which, I think there's a library function that opens a directory and then returns a block of allocated memory. And in that case, there's several different ways that could go wrong. You might have given a bad name that doesn't exist. You might not have permissions, so on. Okay, so there's some systems out there that use negative numbers for errors and positive, negative integers for errors and positive integers for results. We'll see an interface like that later this semester. But the other way of returning both an error and a value itself is is to is to return the value in a parameter. Pass a reference to a parameter, to a variable, and there's one or two allocation functions like malloc, which were basically written by a different set of people who strongly believed that everything should work like this. And those uniformly had a return value that indicated whether it succeeded or failed, and any actual values, and the real return value was stuffed into stuffed into a variable that you passed a pointer to. So you would do you would declare a variable for the return value, and then you'd pass a pointer to that variable. In fact, if you ever look through Microsoft's header files, their C header files, you'll see that they defined two macros which actually disappear when you compile. So they would have defined this as they would have explicitly labeled any of the parameters to a function which were being used for output rather than input. Of course, that being Microsoft, that guaranteed that the people doing the Unix libraries after that point would never do that. So, but that's the thing, is that you can look at parameters to a function like this as there's input parameters. In this case, it's saying something about the memory that we wanted to allocate. And there's an output parameter, which is a pointer to a variable. And if everything works right, this is going to stuff a value in there. So those are the two. So this lets you explicitly return a value, a status indicating whether something succeeded or failed, and a value. Here, we're implicitly doing it by separating the space of possible values into legal ones and illegal ones. Now, you can probably get through an undergraduate CS degree without ever writing code that actually does a lot of error checking or worrying about that sort of stuff. But the way that but in general, production code needs to do something about errors. The applications that we use, day to day, typically are checking the values of, anything that could reasonably go wrong. So if you give your compiler a bad file name, instead of crashing, it prints out file name, no such file or directory. If you pass something sufficiently wrong to someone's web application, maybe you'll get a stack trace in your debugger, but the application itself will continue running because in that case, they were using a language that had an exception handling facility. But C doesn't do that, so we have to handle it ourselves, and that means that solid code will have lots of, open this file, check if the open worked. If it didn't, print an error message and do something intelligent, which either means exit or, if it's an editor, you don't want it to exit if you gave it a bad file name. You just want to start all over again, Ironically, this is one that on the machines we use is pretty much never going to fail. If you run out of memory, your computer will run really slow, and eventually maybe, this call to malloc might take a whole long time while it's trying to scrape up that memory. And then if it couldn't, this program might crash or a different program might crash, at which point it gets enough memory. But it's a little known secret that on Linux, malloc never fails. All right. So I'm sure that almost all of you have seen well, is there anyone who hasn't seen the printf function? Okay, so basically, so there's really, it takes a format string and then a variable number of arguments. And the number of arguments had better match up with the format string. The compiler actually checks that. It looks at the format string and will complain if you're trying to print out a string as an integer or something like that. So So, you know, the main things we'd ever print out are an integer or a string. And if you remember, C doesn't have any fancy string objects. Instead, by convention, we use, we use a pointer to character to represent a string, and we expect that the string is terminated with a 0 byte. If your string isn't terminated with a 0 byte, then printf will happily keep pulling bytes from memory until it gets to a 0 and print them out on screen. But if you use the standard string functions in C, then in fact all your strings will be 0 terminated. So the standard library function for opening a file is fopen. It works, basically the open call in Python was kind of borrowed from this. You pass a string, R for read, W for write. It's pretty rare to do read-write. We're going to forget about the binary flag because that doesn't matter on these machines. There's a call to print to a file. There's two functions for dealing with binary data that we're going to forget about. Sorry. What typically the primary function that if you're reading a text file, the C function you would be using is fgetS. Basically you'd have a while loop saying while fgetS is not equal to null, do something. And so here I have what? Let me put this where everyone can see it better. So if you put this into a while loop, while this doesn't return null, then every time through the loop, it will read another line from the file into this variable here. And again, this is using the caller allocate pattern, where we have to allocate memory to put, to read data into. In this case, because we don't have to allocate a whole bunch, we just have a local variable. And so, this code like this is probably found in, zillions of C programs that, process lines of text. At some point, you probably want to close a file descriptor. Okay. Now, I may have gotten these two backwards. String compare is an annoying function because you almost always just want to check whether two strings are equal. So occasionally I need to remember what the non-zero, which way the non-zero return values work, and I have to go and check the documentation every time. So you certainly aren't going to need to determine if one string is greater than or less than another in this class. So now so why can't we just use the equality test in C to compare two strings? Let's see if we can get someone. Yes. Yes. In other words, okay, in this case, if they're both pointing at the same string in memory, it'll be fine. if they're pointing to strings that are equal but not the same, two different locations in memory that each contain the same string, then this is going to return false. Because C doesn't have real string types. It just has pointers. It knows how to compare pointers. We've constructed this whole house of lies on top of that, that treats character star pointers as strings, but under the hood, it's just two pointers. And so if we want to see if two strings are equal, we're going to have to use string compare. Especially because if we have a constant string we're looking for, that's guaranteed to be at a different location in memory than some, variable that we're putting input into. So we'll want a comparison there. And there's various ways to copy strings around and do other things like that. But honestly, there's a variant on the printf function that takes a character star pointer, pointer to a buffer, and it prints into it. So you give it a format, and it fills this out. Yes, it doesn't take a length on that. That's evil. But in general, for the types of things we're doing in this class, that's fine. And then this is the reverse of printf. It takes a string and a format. It matches the format to the string, and it stuffs, it's an unprintf. If x and y had 5 and 6, well, if I was doing sprintf, I might have created this string 5, 6. scanf will reverse that process and use this format string to pick it apart and stuff it back into these variables. And between these, you can probably do, well, you can certainly do any more than enough string handling for this class. And if you're, you know, if you're stuck doing significant string handling in C afterwards, you know, my condolences. Yes. Yep. I'm sorry? No. Okay, there's, so scanf reads from a terminal. String scanf reads from a string. Honestly, if you're reading from the terminal, you may want to actually save the line and then split it apart, because that way you can, it makes it easier to complain if the user did something wrong. But, you know, that's enough string handling in C, because in general, my advice for string handling in C is to use a different language. All right. So the rest of the lecture is going to be about I/O virtualization. And when I say virtualization, set your sights very low. We're not talking about fancy virtual machines and things like that. We're just talking about the fact that, you know, most operating systems, well, for instance, that when you use printf, you don't care whether you're logging in via SSH, whether you're on a terminal in the, you know, graphical user interface, you know, or you're on a text console. It all works the same way. You just do printf, you know, or, you know, you can redirect the output of something to a file, and it works the same way using the same system calls, whether, you know, it's writing to the terminal or writing to writing to the file. So if you remember, we had, you know, we talked about a couple of really simple devices on, you know, on our toy computer, a frame buffer and a keyboard interface. And we had, you know, well, you know, we could, you know, if you remember, it was basically a big block of memory where each byte in memory corresponded to a position on the screen. And if you wrote a character to one of these positions on the screen, then one of these positions in this frame buffer, then the corresponding character would show up on the screen. Unless you wrote, maybe it would be a funny character if it wasn't a printing one. But now, I'm certainly not going to put it on the on the blackboard, but it wouldn't be hard to to keep a couple of variables for where the current cursor was. And every time you write some, and have a write function which takes the bytes and looks at them and says, is this a regular character? Okay, put it in here and bump the cursor forward. Is it a new line? Okay, calculate the beginning of the next line. And so on. Similarly, we could have a read from keyboard function. We might want to let it read multiple characters, but it's probably a good idea to have it return when you hit new line. If you ask it to read 100 characters and you hit 2 characters and then return, you probably don't want your program to be waiting forever. So this would basically read a line from the keyboard or this many bytes, whichever is shorter. Now, if you remember, we had I could define a structure that had, a file name, a length, and a starting block, and make an array of these structures and use it as a directory. And so I could now Now I could write a function which I give it a file name, it reads through this directory, and it gives me, a structure saying, here's the starting block of the file, here's the length of the file, and here's our current position in the file, 0. Now, I could write something very much like a Unix read system call, which took a buffer in length to read into, and took this internal file structure. Because from this, we could calculate exactly where we need to read from the file. It would start off with position 0. And then if I go to read 100 bytes, well, it'll read the first block of the file, copy 100 bytes, and then update this position. And if I ask to read 100 bytes again, well, because it's very dumb, it'll go and it'll read that first block again and copy the second 100 bytes and update the position. And if I read across a block boundary, it'd be a little tricky, but it would update the block properly and read and so on. And if it reached this file length, which I found out from the directory, then it'll return something saying this is the end of the file. And so here we've gone from a really simple layout on disk of just, a table of file names, lengths, and starting blocks, to a read function, read from file that that we can use in our program, in a fairly civilized fashion. The problem is that we don't have like a general purpose I/O abstraction here. Here we're still saying this is a file. We can read from the file. This is a keyboard. We can read from the keyboard. We can write to a frame buffer. We can write to a file, although it's really painful. We'll see later why we probably want a fancier directory for that. And, if it was the mid-60s and you suggested doing anything to deal with this complexity, you probably would have gotten a lot of, engineers arguing, but they're fundamentally different. You have these options for this and these other options for that. Turns out it doesn't matter. It's worth, not being able to use those options a lot of the time in order to make everything work the same way. So, Now, C doesn't have classes and interfaces, and we've only just started using C, so I'm not going to show you the ugliness that's needed to fake them. But most of you have probably seen, again, interfaces and virtual class, and an inheritance in other classes. So if we could define an interface that had write and read, and now we have we have like a terminal class, which is an instance of that. And its write function writes to the frame buffer. Its read function reads from the keyboard. And now we have something where, inside the operating system, we can have a uniform way of, of reading and writing. We can have in particular, one way we can do this is, we can have an integer file descriptor, and then inside the operating system, we can have a table where the entries in this are pointers to, this superclass. So we're going to have, and if we're going to follow the Unix model, we could say we have a standard in, a standard out, and a standard error. And those we're all going to initialize to a single instance of, term IO that's pointing at our terminal. Now, if we open a file, and note that this is using the low-level open call. This is the system call. It's, you can't do anything. It gives you back an integer file descriptor that you can't use with any of those fprintf functions or anything. You can, Yeah, the file I/O is also going to need to save this stuff. So, we can, when we open the file, we can create an instance of I/O stream, which happens to be a file I/O instance. And, as part of open, we looked up file ABC. We got the information from the directory. We put it in, we put it in the structure. And now, our read system call just has to look up that object in the file table and invoke its read method. And this is basically how Unix I/O works, is your process has a file table in the kernel, and that file table has pointers in it to structures which vary depending on the type of I/O stream it is. If it's a network connection, it'll have one set of information. If it's an open file, it'll have a different set. If it's if it's going to, the physical console, keyboard, and frame buffer, which you almost never see nowadays unless you, drop your VM into text mode so that, and you access it by SSH, so you're really not using that. But anything that you talk to by a file interface is going to have a class that's a subclass of, I think in Linux it's called struct file, very showing much originality, but that has everything that inherits from that has to provide a read and a write method. And you call the read method with a buffer and a length, and it reads data into it and returns, and obviously they all have the same semantics for return values and so on. So what this lets you do is, this trick inside the file system inside the operating system, lets us write code that doesn't care if we're writing to a network connection, to a file, to the terminal, or whatever else. Questions? Under the hood, it's implemented, because it's in C, it's implemented with function pointers and other ugly things. But again, it works the same way as a virtual methods in C++ or similar facilities in other higher level languages. And All right, there's 2 minutes left. If you have questions, you can ask me, and we're done for the day. And I've got office hours this afternoon. Feel free to stop by, even before or after the scheduled time.